Okay. Oh, so welcome everyone. We're gonna have one more session of our brag today with a special guest, Israel Vainsencher. He's gonna talk about enumerative geometry of Legendrian foliations. It's a pleasure to have you here, Israel, really. And so the word is yours. And, well, go ahead.
Okay. So let me start thanking a lot the organizers for this invitation. It's a real pleasure and an honor. And I can just say, to summarize, that I'll be talking about a little more of the same, in a sense. Okay? So please interrupt me as often as you feel like. Is this visible? Yeah, I think it is, right?
Yep.
So there is no red over the flag. It's at the side. Okay. So I'll be talking about enumerative geometry of the so-called, not legendary, but Legendrian foliations. And it's a tale of contact. So let me start by recalling to people which are not specialists, as myself, what is understood by a foliation, specifically in this talk. I'll be talking about foliations and a little more generally, some sort of distributions. And these are concepts which provide a geometric viewpoint in the theory of differential equations. So the foliations of dimension 1, they are the geometric counterpart of ordinary differential equations. And distributions, I've been told, it has to do with the partial differential equations. But our approach is entirely geometric. So grosso modo, informally, a foliation of dimension 1, I'll be always talking about foliations of dimension 1, is a polynomial recipe to draw a line at each point. Okay, so that's just as expected. And our ambient space is projective space, just to make it as concrete as possible. And now let me talk about the kind of distributions that will interest us. A distribution for us is a distribution of planes. So codimension 1, subspaces of P3. So as the picture shows, the distribution of codimension 1, you attach a plane at each point, containing the point. We shall assume, for most of the talk, that the coefficients of the equation of the plane are functions of degree 1. So that's the equation of a plane, and the AIs are functions, are polynomials of degree 1. These are, as I've been told, what people call distributions of degree 0, as simple as possible. Now, if you look at the expression sum AI xi equals 0, you can think of this as a syzygy of the xi's. I'll show in detail in a few minutes that the distribution will be associated naturally to an anti-symmetric 4x4 matrix. And those which have an associated matrix with non-zero determinant are the so-called distribution of contact. I'll be more explicit about that in a moment. And a foliation is called Legendrian when it's tangent to some distribution of contact. So you fix a distribution of planes, okay, and you give yourself a foliation of some degree, and you are interested in the condition of contact among the foliation and the distribution. So our goal here is to describe the calculation of the dimension and degree of the subvariety of Legendrian foliations and friends. In fact, I'll be talking essentially about one additional friend in this situation. And it turns out that the answer for the degree in the cases we treat here are given by a polynomial which is to be called an Atus polynomial, more ahead. So that sort of mimicking Schubert calculus, instead of applied to planes and lines, etc., it will be applied to foliations and distributions. So let me start by saying that this is joint work with Mauricio Correia. And for details and further motivation, I'll leave these two references, which are in archive. And I've also learned a lot by just chatting with Jorge Vittorio, Alain Muniz, and Fernando Kuckerman. So let's start with pictures. Another plane. So that's a distribution of planes of a special kind. You change the line, you get another distribution of planes. If you take the intersection of these two distributions of planes, you get a foliation of dimension 1. So you think of the red line here as the intersection of the blue plane and the black plane attached to this particular point. Of course, there are points where the foliation is not defined, and where the distribution is not defined as well. If the point is on the line, the plane is not well defined. So singularities are allowed. So these are distributions of the kind which are called pencils. So these are pencils of planes. One could also talk about pencils of quadrics. It's harder. I'll have a word on that towards the end. So these pictures here correspond to distributions of the form pencil of planes. You change the line, you change the distribution. In the expression for this distribution can be given by a differential form, a one form of degree 1. That's the degree of this one form here. U and V are polynomials of degree 1. And you can think also of the leaves here as level sets for the pencil defined by U and V. So let me draw now another recipe to choose a plane through each point in tree space. It's as simple as possible. Given a point, say in affine coordinates, you take the equation of the plane as y minus y naught, z naught x minus x naught z. Of course, this point is on this plane. Okay? So you make a correspondence, point, plane, and the point lies on the plane. Correspondence between points and hypersurfaces such that the point lies on the hypersurface. So that's a linear null correlation. In homogeneous coordinates, you take this point here in tree space, and associate this plane, which obviously pass through the point. What is not so well known is that this naive distribution here is related to a classical synthetic construction, which involves a twisted cubic, which, as we all know, is the most loved rational curve in space. So here's the association. Take a point into space. Associated to this point, there are 3 osculating planes passing through P. So that's one osculating plane. There are 2 other osculating planes. And there are 3 points of oscillation, as you see here. You take these 3 points of oscillation and connect them by a plane. They span a plane. And that's, surprisingly, a plane that will pass through P. That's an exercise in symmetric functions. I'll give a reference for that in a moment. Okay, so repeating. Fixing this twisted cubic, for any point, you can find 3 osculating points on the twisted cubic, which will span a plane. And that's the correspondence, point, plane. And conversely, to each plane, you can take the 3 points of intersection, draw the 3 osculating planes at these points, and sure enough, they meet at 1 point, as you expect of 3 planes in space, and the point lies on the original plane, red plane. Let me just translate, copy this sentence. The points on the cubic curve correspond to its osculating planes, and inversely, so that this cubic curve is self-reciprocal in this polar system in space. That's classical. So this was found and explained by one of the inventors of the alternating current, Charles Steinmetz. He is one of the founders of General Electric. He was a colleague of Tesla's. He liked mathematics. So summarizing, we've just learned a classical so-called null correlation in 3 space. To a point, you associate a plane using the osculating planes to twist a fixed twisted cubic. I love this figure, this picture. That's classical. And you can find the details in Sample and Kneebone. That's a classical, it's a beautiful book. And I have to thank Ragni Pine. It's my pleasure thanking her. She's who told me about these stories of null correlation and so on. That's special for Leterio. Leggere il classici è meglio che non leggere i classici.
For Andrea.
For Andrea, yeah.
Appreciated.
Yeah. So in general, a distribution of planes is given by projective one form. So it's you can think of one differential form in C4, okay? But it induces what one calls a projective one form, provided the coefficients here, which are taken as homogeneous polynomials of degree n+1, satisfy this relation. So it's a syzygy for the coordinates. So given this differential one form, you associate the plane, plugging in the point in the coefficients. So that's the equation of the plane associated to the point P. And then we call the degree of the distribution the number of tangencies with a general line. And we'll see in a moment, just as an exercise, that the degree is m. So if the coefficients are polynomials of degree m plus 1, if you take a general line in P3, there will be m points of tangency. So if you take a one form and interpret this sheaf as the dual of TP3 twisted by this line bundle, so it's home of TP3 to this line bundle. Given omega here, we have a map from TP3 to this line bundle. Okay, and then you pick a general line. The number of points on the general line which will kill this differential form is precisely n. You just complete the diagram with the tangent maps, and you see that in order that the tangent to P1 at the point lie in the kernel of the differential form is the same as requiring that this map here be 0. So you get a section of OM over P1, which has, of course, m zeros. Now, let's look again at the condition that defines projective one forms. So that's what one calls a syzygy of the homogeneous coordinates. So here's a simple syzygy. And it turns out that the syzygies of the regular sequence x1, x4, in fact, for any regular sequence, the only syzygies are the linear combinations of the so-called Koszul syzygies or relations, which presently are just 6. So this number 6 here is the same number as the dimension of the space of anti-symmetric 4x4 matrices. More in a moment. So when we look at one forms of degree m equals 0, which will be of interest to us, which is the case of pencil of planes and the null correlation that we talked in a moment ago, the AIs are linear forms. So these are linear syzygies, okay? So the syzygy can be written as a constant, a combination with constant coefficients of the basic Koszul syzygies. There are 6 of them. And I make the association of this syzygy to this differential one form and to this bivector. Okay? Relate them 3. So you can rewrite the one form as a combination of these basic one forms. And you see that the one form corresponds to this anti-symmetric 4x4 matrix. And also corresponds to a bivector in wedge 2 S1. And we say that this differential one form is a form of contact when this associated anti-symmetric matrix is non-singular. That's the condition. So we have a space of distributions of degree 0, which is a P5. Okay. And now think of the points of P5 interchangeably as one form of this kind, or a 4x4 anti-symmetric matrix, or a bivector. So this P5 here is the parameter space for a family of distributions of degree 0. Among them, there is a distribution which corresponds to pencil of planes, and there is a distribution which corresponds to contact forms. So if we go back to our linear algebra, we recall that the rank of a 4×4 non-zero anti-symmetric matrix can only be 4 or 2. So up to change of coordinates induced from the change of coordinates in P3, there are just 2 possibilities. That's rank 2, which corresponds to this one form, which corresponds to a pencil of planes. And there is the contact distribution, which makes up the open orbit. So for this one is pencil of planes. For the other one is the null correlation. So there are 2 orbits. The open orbit is contact forms, which correspond to indecomposable bivectors. And the closed orbit is a hypersurface. It's the quadric of, it's the Plücker-Pfaff quadric. Okay? If you compute the determinant of that 3×3, 4×4 antisymmetric matrix, it's the square of the equation. I mean, if you look at the 2×2, the 3×3 minors, which are cubics, okay, you see that what you get is actually the Plücker quadric, which corresponds to integrable one forms, or decomposable bivectors. So if you take a 4×4 antisymmetric matrix and ask that it be singular, the rank drops to 2, okay? And the 3×3 minors generate a principal ideal, okay? Which is the cube of, it's related to the Plücker quadric. So what we are going to work out here today is the relation between foliations of dimension 1 and distributions of codimension 1 of the type I've just talked about. The foliations will have arbitrary degree, but the distribution will be fixed to be of degree 0. And we'll study the condition of nesting. So I want this foliation to be tangent to this distribution as indicated in this picture. And let me just recall that the ambient space is P3, and this 3 could be replaced by any odd higher dimension, but things get a little complicated. I'll talk about a little more about that later. So foliation of degree D, dimension 1, is just a choice of 4 polynomial, homogeneous polynomials of degree D. And you think of them as coefficients making up a vector field. So the game here is that for each point, you compute the image of the point by these polynomials, and you join the line. So the line associated to this red point here joins to the value of this polynomial map here. Of course, you can change the polynomial map without changing the distribution. You just add a multiple of the so-called radial vector field. So the Plucker coordinates that you compute from this matrix are exactly the same as the ones we compute for this one here. Okay? There are some singular points where the foliation is not defined because this matrix here could be of rank less than 2. That's almost unavoidable for foliations of dimension 1 in P3. And so you see that the space of foliations is this big projective space where you take the homogeneous polynomials of degree d as coefficients of these differential forms. I'm sorry, differential operators, partials with respect to the variables. So this n here is given by these binomial coefficients. I'm just counting the number of monomials. There are 4 of them because I'm taking this tensor product here. So a typical element in the numerator here is a polynomial vector field. But since we're looking at it as defining a foliation, we actually take its class mod multiples of the radial vector field. And that's the plan for the rest of the talk. We want to impose the condition of tangency of a foliation of a given degree, tangency to distribution of planes. We can talk about distribution of planes in general, but we'll concentrate very soon in the case of degree 0. So that's as a motivation, we could think of this as trying to do some Schubert calculus for, I think Kleiman used to call pan-algebraic sets. I heard the word, the terminology pan-algebraic sets from Kleiman, some maybe 10, 20 years ago. So a foliation tangent to a fixed distribution are the foliations for which the inner product here, or contraction, is 0. So for fixed A's, for fixed omega, this is a linear condition on the foliation. So this omega d perp is a projective subspace of the space of foliations, which I'm denoting by FD. So there is some similarity here with the discriminants of hypersurface. You first fix a point, and then you require that the partials of the equation of the hypersurface vanish at that point, and then you vary the point. So the discriminant, as we know, is rolled by linear spaces, just as the family of foliations tangent to a distribution will also be, in that sense here, be ruled by these projective subspaces. And then we'll move the distribution in a suitable family. I'm always thinking precisely of one of these two families, pencil of planes or null correlation. For the time being, at least, are the only two kind of distributions for which I can say anything with some safety. So that's what we want to study. It's the space of all foliations of degree D tangent to some distribution varying in a family. And that's just a first approximation. Be clear in a moment why it's only a first approximation. Would love to say something in general about expected dimension. And of course, our aim is to compute, to say something about the degree of this d hat. Now, the problem is that as you vary omega, as you vary the distribution, the space of foliations orthogonal to distribution, the dimension jumps, as we'll see in a moment. So that's the difficulty. It's almost everywhere plagued by wrong dims. Wrong dims is something that forbids us to use techniques of intersection theory. So, as we're doing with the case of discriminant, we look at the correspondence, a distribution and a foliation, which is orthogonal to this distribution. So that's the natural guide to look at, because the equation here is bilinear. Okay. So we'd love it if first projection, that means fixing omega, if this were a projective bundle. That's what would be lovely. But it doesn't happen very often. It's very hard to control the dimension of the fibers here. Now it's clear that this correspondence is closed. I'll talk a little more about the equations in a moment. The fibers of P1 is just the orthogonal of the distribution. The image is that union of all foliations tangent to some distribution in the family. So it's closed because it's the image of something which is obviously closed. Now the equations here, you see, you want this to be 0 for all x in P3. So there is sort of an elimination of a variable when I write this equation here. So in general, what we'd like to do is this. You fix some family, take some closed irreducible subvariety in the projective space of all distributions of degree m. So we have a tautological line subbundle here. Okay. That's the trivial bundle. And then you compose to the cotangent bundle twisted by m plus 2. That's just restriction of global sections. And you look at this length arrow as defining a map from TP3 to OM plus 2. So that's what defines the universal twisted differential form. So it's a map from TP3 to OM plus 2, twisted by the tautological hyperplane bundle of D. And you can do the same thing with the foliations. You can look at the universal foliation. So the universal foliation is given by the section of TP3 which arises from this diagram here. So if you recall the universal differential form that we had in the page before, we can just put these two together. So now we have a map from this line bundle to this line bundle here. So the correspondence defined by taking a distribution, a foliation, and a point, and asking that the evaluation be zero is defined by the zeros of this section here. So this section here, which is obtained by composing the universal vector field with the universal distribution. I'm calling this sigma. It vanishes as a point precisely when this orthogonality here holds. So the correspondence that you defined a few moments ago is just the scheme of zeros when we eliminate x here. So it's the scheme of zeros of this section sigma along the fibers P3 of this projective map here. Okay, so it's the pair of points omega phi such that omega x phi x is zero for all x. So you want it to be zero when you restrict to the fibers of P3. So that's pretty much the setup that Altman and Kleiman used to study Fano schemes. The correspondence, the tilde D, is the scheme of zeros of the so-called adjoint section that we have here. The problem now is that the zeros of this section are wild. I mean, they don't have the correct dimension in general. I'll show you why in a minute. So that's the difficulty to be dealt with here. You see, if you fix omega in phi, we're taking this inner product, what we get is a polynomial of degree d plus m plus 1. The ai are coefficients of the differential form, have degree m plus 1, and the phi has degree d. So you take this inner product here, you get a polynomial of degree d plus m plus 1. So let denote by j omega this homogeneous ideal, the ideal generated by the coefficients that define omega. And sub k will denote the homogeneous part of degree k. So when you fix omega, the vector fields tend to this fixed omega, they form a vector subspace, which is the kernel of the evaluation map. It's the kernel of this dot product map here. And now it's clear that the dimensions here will jump when the rank of this dot product here for omega fixed jumps. So we need to control the dimensions of this homogeneous piece, of this homogeneous ideal. And I can only do this, at least for now, when m is 0. So when m is 0, we can ensure that this phi d here will be a vector bundle, will be the fibers of a vector bundle, which I'm denoting by a tilde. I'll explore the two situations that I talked about, pencil of planes and null correlation. Pencil of planes is the most elementary, is the easiest one to understand what's going on. So my family of distribution here will be either the whole of P5 or the closed orbit, which corresponds to pencil of planes. You see, when you take the pencil of planes, and if you compute all evaluations possible here for arbitrary PI, you can convince yourself that what you find is a piece of degree d+1 of the ideal which defines the line x1 equals x2 equals 0. So evaluation here has constant rank. On the open orbit, it's clear that we also have constant rank. In fact, over the open orbit, we get all polynomials of degree d+1. I mean, you see, if you take this representative of the open orbit, you'll replace the x2, the x1, the x4, the x3 by arbitrary polynomials. So you will be computing an arbitrary combination of the homogeneous coordinates. So you get all of SD+1. Foliations tangent to a pencil of planes. So in this case, the image here has constant rank. It's just the polynomials of degree d+1 which vanish along the line. So the rank of the map is independent of the one form that you take. And the image is precisely this here. U and V are generators for the equation of a line. And our J is just the kernel of this surjection. So we can now build that vector bundle phi tilde in the case of pencil of planes. So the pencil of planes are parametrized by the Grassmannian of lines. Okay. Now here we have the map of dot product against the coordinates of the vector field. I'm calling P the image sheaf. This is the kernel of this evaluation. So you see that P is a vector bundle with rank very easy to compute from this here. This what we have this twist here, which arises from this from the diagrams involving the universal differential form, universal foliation. So there's a twist by the Plucker line bundle. So if we we call the space of foliations of dimension n in degree d. The image in the space of foliations of this projective subbundle, okay, so that's the kernel here. See, here is the foliations, which when you make the dot product against omega, you get 0. So you get a projective subbundle here. It projects to the space of foliations, and you get the set of foliations tangent to a pencil of planes. So that's a nice projective bundle, and that's the image of that projective bundle. And in fact, this projection map here is generically bijective, at least for d bigger than 1. The case d equals 1 can also be handled, but there is a trick. It's not worthwhile talking about it now. Wait for the preprint. So that's a very happy situation. I want to compute the degree of the map, of the image of a projective subbundle of a trivial projective bundle. So just from general principles, which I'll recall in a minute, this degree here, the degree of this family of foliations tangent to a pencil of planes is given by the top dimensional Segre class of that vector bundle defined in the transparency before. So that's pretty much the definition of Segre and Chern classes a la Fulton. We have a projective bundle here, that's the Grassmannian, and it's the image of this P here that I want to compute the degree of. You see that since this is generically bijective, we can compute the dimension. This dimension is known, it's just some binomials. And to compute the degree here, you take the hyperplane class, cap it against the appropriate dimension or hyperplane class. So the degree of the variety is the degree of the zero cycle. Since it's generically bijective, I can make the computation of the zero cycle upstairs using projection formula. Okay. And once you have a zero cycle up here, you can compute its degree, taking the push forward under Q. And that's where Segre classes arise. So this is pretty much the definition of the fourth Segre class. And you can make the explicit calculation. You have this vector bundle. This is a trivial bundle. So the Segre of this is the Chern of that. Okay, because in the middle, it's a trivial bundle. And the Chern of P is computed in the Grassmannian. Okay? So everything is so explicit that you can just run Schubert. Okay? Use Schubert for Maple, which is the one I know how to use. So you construct the Grassmannian of two quotients of a four space. I'm denoting by Q the indexing of the Chern class of the tautological quotient bundle. Okay. So that's the Plucker line bundle, which is the top wedge of the universal quotient here in Schubert notation. So that's that phi tilde, which can be computed due to the exact sequence where it fit. Okay. Don't forget to twist by the Plucker line bundle. And then you compute the top Chern class, compute the integral. You can factor it. It's a nice polynomial. And then I call this polynomial by the name of etus. Okay, and we can do something explicit here. And if you care, we can copy and paste this into a session of Maple. It's already open, so just paste it here, and it's computed. Here is the answer for the polynomial. These are the first few values. Now back to the general exposition. Okay, that's Atus. He's my adoptive grandson, son of Mauritius. And that's the polynomial already factored. So that's the case of pencil of planes. Now the case of Legendrian vector fields, there is a slight twist. How much time do I have?
I think half an hour.
I won't need that much. I think I'll need some 15 to 20 minutes. Okay, so let's go on to the case of the title, Legendrian vector fields. So as I said, these are the polynomial vector fields which are tangent to distribution of contact. So recall that's a distribution of contact. The alpha ij here are constants, and the determinant of the matrix, anti-symmetric matrix alpha ij, has to be non-zero. So it's in the open orbit in P5. For instance, this one here, which appeared in the example of the null correlation a while ago. And here's an example of a Legendrian vector field. If you evaluate omega on this vector field, you can see everything cancels and you get 0. Now, let's do some multilinear algebra here. So in the vertical here, I have the tautological line sub bundle of the wedge 2S1. So this selects the anti-symmetric matrix, so to speak. Okay? So the sigma should be thought of as the universal anti-symmetric matrix. And the map here is explicitly given in terms of the partials that appear here. So that's the universal 4x4 anti-symmetric matrix. Now, if you think of it as a bundle map, the kernel as a sheaf is 0, because sigma is generically an isomorphism. So the kernel must be torsion, and this is torsion-free. So the universal anti-symmetric vector bundle map is injective as a map of sheaves. So the image here is a vector bundle, isomorphic to the domain. It's not split in the image, in the contour domain, but it's a vector bundle. And the rank drops from 4 to 2 precisely over the Pfaff-Plucker quadrant in P5, which is given by the decomposable one forms. Now let's play with the foliations here. So that's the universal anti-symmetric map. You tensor with SD in order to have polynomials of degree D. So that's just tensoring with SD. And then here you take multiplication. You end up with degree D plus 1. So this decomposition here can be thought of as the universal dot product of distribution against foliations. Okay. Now the main technical difficulty for me is to have a smart, educated way of computing the Chen classes of the image of this map. Notice that it is surjective on the open orbit, because this here is an isomorphism on the open orbit, and this map here is surjective. On the other hand, the map sigma drops rank schematically along the hypersurface. So the same thing happens when you twist it by SD here. This drops rank along the same hypersurface. So the composition drops rank exactly along the same hypersurface. So if you play around with fittings, you should be convinced that the image of this map here, which is the image of this red slant arrow here, is a vector bundle. Okay? And everything here is so explicit that it should be easy to find the Chen classes of the image of this map. Unfortunately, I don't know how to do that. So I had to take a different path. Of course, I want the Chen class of the image because I need the Chen classes of the kernel, which is what defines the Legendrian vector fields. The composition gets 0. So that's the main technical point here. The image here as a sheaf is locally free, though not locally split. So it should be not so hard to compute its Chen classes using Macaulay, for instance. Okay? And then trying to deduce how to do that in general. Now, of course, the space of vector fields is the quotient of this by that. And the composition here kills the denominator. So it passes to the quotient, and it's the kernel, essentially the kernel of this map that controls the Legendrian vector fields. Just to recall, we're taking dot products, and the map is surjective of the Pfaffian. So you can take the kernel, since the image is a vector bundle, the kernel is a vector bundle, okay? I twist it back by O1 in order to have it as sub-bundle of the trivial vector bundle of all foliations of degree D. So as I said, the kernel is a vector subbundle, of course, over the open orbit, but it extends, okay? It extends as a vector bundle over all of P5. And the reason is that, as I said, the rank drops schematically along a hypersurface. So just to recall, LD is a set of pairs, foliation, distribution such that the dot product here is 0. And MD now is the image. So I need to compute the chain classes, be it of MD or of LD. One gives the other. And again, if you look at the space of all foliations, the same sort of diagram that we had before for the case of pencil of planes we have here, except that now instead of the Grassmannian, we have the full P5. The image here is the set of Legendrian foliations, and it's the degree of this image that we want to compute. So just as before, it can be shown that this map here is generically bijective. So we get the same dimension here. And then we can use the same argument as before to compute the degree as a top Segre class. Now it's a fifth Segre class because it's P5 instead of the Grassmannian. Okay. And for the actual calculation, I need the Segre class of that. It's the same thing as the Chen class of that because in the middle, it's a trivial bundle. And since I was unable to compute the Chen classes directly, I'll resort to the toolbox of Bott's formula in equivariant context. The point is that even though I don't know how to compute directly the Chen classes of MD, I know how to compute the fibers at the critical points, at the fixed points, okay? Just as required by Bott's formula. So we need the description of the fibers of that image sheaf over the 6 fixed points. It's 6, that's a P5, and you have 6 fixed points, which, no surprise, are just, let's say, the canonical anti-symmetric matrices of rank 2. So I need to compute the fibers of MD for sufficiently many Ds, let's say, at these fixed points. Let's pick one of them and work it out. Not too many details, but just to give an idea that everything is hands-on. So this fixed point corresponds to this one form which is integral, which corresponds to a pencil of planes. That is the plane with axis x1 equals x2 equals 0. And then, in order to compute the fiber of MD, we perturb this one form to full rank. So we'll add here a term which pulls this one form away from the Pfaffian. So if set t equals 0, we get the point over which we want to compute the fiber. So what we do is we compute the fiber for general t and pass to the limit. We evaluate omega t on vector fields of degree d. This will give us a vector space of the correct dimension because it's full rank. The correct dimension, I guess, is d+2 or something like that. And then you take the limit as t goes to 0. So let's say that d equals 2 to make something as explicit as possible. So we start by constructing a basis for the vector fields of degree 2, which will be fixed by the C star action. In a general recipe, which I learned a couple of weeks ago, again, Mauricio, I think it was either Mauricio or Alain that explained me how to do this. You compute the vector fields with 0 divergence. So you take a general vector field here, okay, and compute its divergence and set it to 0. And it turns out that this subspace here is a complement to the multiples of the radial. So since our vector field is the quotient of this by the multiples of the radial, we get that this here give us nice representatives for the vector fields. So the vector fields of degree 2 are represented by vector fields, not just classes, with 0 divergence. So we need a basis for the kernel of this map. So we know a basis for this domain here, of course. And then it's a problem of linear algebra, which isn't so hard to see how to work. Okay, so you can find an explicit list of 36 vectors, of which it only interests us what we call the weight. So there was the action, so x2 squared has weight 2 omega 2. This operator has weight minus omega 1 because it was in the dual, if you recall. The delta xi are a basis for this S1 upper star. So you get weights for elements, homogeneous elements in the basis. So the elements that are built here, they are all eigenvectors for the C star action at play. And then you compute the matrix of the map. You see, we end up in degree 3 by the dot product, right? We have polynomials of degree 2, dot product a form of degree 1. We end up in degree 3. So this is computed explicitly. Of course, you do this using singular, for instance. That's what I did. So we compute the matrix of this map here. And you do this by saturation in the following sense. You have a matrix, you perform operations, row operations on the matrix. You divide, whenever possible, by the GCD. And at the end, you set t equals 0. That's what saturation means. Okay? This is done algorithmically. And in this way, you get a matrix with the correct rank, which is 20 presently. So the columns of the pivots of this matrix form a basis for the fiber at the fixed point. As you know that the columns of pivots generate the image. That's what we want. Okay. So that's not very instructive. It's just to say that it's possible to put your hands on and compute. Then you find a list. You make it numerical. So that's the list of the weights. You make it numerical, choosing numerical values for the W's. So I'll set W1 equals 0, W2 equal 2, etc. Okay. So this list becomes a list of 20 numbers. So this 23 here is tries 10, that's 30, minus 7, that's the 23. Likewise the 10 and so on. And then the equivariant top 5-dimensional Chern class is symmetric function on these numbers. Okay, so I have to compute the 5th elementary symmetric function on this list of numbers. Precisely, you take x plus 23, x plus 10, etc., multiply throughout and collect the coefficient. Of course, you do this all mod x6, and you collect the coefficient of the x to the 5. That's the 5th Chern class. And you get some number. Now, what bot formula says is that the degree I want to compute is a sum of contributions at each fixed point. And it's explicit some numbers like this here. And you compute and you get this positive answer, okay? And that's precisely the value of a new Entails polynomial, precisely for d equals 2. There is Entails again, okay? It's gotten by interpolation. And the first few values are this one here. Now, just one observation. If you compute the degrees, if you look at the degree of the answer here, he's 7 plus 8, 5, 15. So that's degree 15, which is 5 times 3. The previous polynomial had degree 12, which was 4 times 3. 4 was the degree of the base there. 5 is the degree of the base here. So my conjecture is that the answer in general will be thrice the dimension of the family of distributions you want to impose tangency to. Okay? So it's just to say that there is something to hope for further inquiries. Now, just to get to the end or close to the end, instead of P3, it could have moved to P5. Then we'd be looking at the 6 by 6 anti-symmetric matrices. They make up a P14. And now the rank can fall to 4 or 2. Okay. Now, where the rank 4 falls to 4 is again a hypersurface. So it doesn't spoil things. But where the rank falls to 2 is a Grassmannian, in fact. It's a Grassmannian of lines in P5. So I have to blow it up first. So if you blow it up and reason very close to what we did to the case of foliations in P3, we can produce some numbers. So we're able to produce the first 3 numbers. But it takes a lot of computations. I mean, it took almost a week to speed up these 3 numbers here. Okay. So for a general case, there is the geometry behind of complete anti-symmetric maps. That's what is going on here. You have to make the appropriate loci to become hypersurfaces, and then the saturation will work, and we'll be able to compute fibers, just as in the case of P3. I think what we've done here for the case of pencil of planes can be reproduced for the case of pencils of quadrics. There should be a blow up there, because pencil of quadrics can degenerate in some sense. So that's work to be done. And thank you.
Well, are there any questions, any comments, remarks? Are
So
there any?
Israel,
Yeah?
you mentioned the twisted cubic, but then you didn't mention it anymore. So it doesn't show up in the computations or in the approach?
I mean, the twisted cubic appears just as a glyph, in the sense that the null correlation bundle, the null correlation distribution, okay, which was given by those alternating equations, looked something just formal, but it has geometric content. And surprisingly, the content is just that it can be defined through oscillating planes with twisted cubic. That's all I know in the situation.
Okay. Okay. Well, thanks for the nice talk. And may Athos live as long as those big numbers.
I'm sorry?
May Athos live as long as those big numbers.
Well, are there any more questions? Well, so if there are not...
So, sorry, I have a question
All right.
for Israel. Israel, you mentioned that you work on families of distributions. Do you assume that these families are flat for things to work out, or this is not necessary?
I mean, the 2 examples I worked out, we had flatness, right?
Yes.
And the other example I mentioned of, say, pencil of quadrics, flatness fails for pencils with a common, with a fixed component. So this has to be blown up. And I think that if you blow up that, maybe things work nicely. I haven't made the computations in this case.
Okay, thank you.
I have a question, Renato.
I think that flatness fails for members with double hyperplanes as fibers.
I'm sorry, I haven't heard.
I think flatness fails also for members, for pencils with double hyperplanes as fibers.
For what as fibers? I'm sorry.
You're talking about pencil of quadrics, right?
Yes, yes.
Double hyperplanes.
Yeah,
So
I mean, I think that what one has to do is to mimic what was done to produce the Hilbert scheme component of elliptic quartics, which required two blow-ups. First, the blow-up where the MCD is non-trivial, and then one additional blow-up to take care, of the plane degenerations. Maybe it reflects in the double hyperplane, as you said. Okay. When an elliptic quartic degenerates to a plane quartic, okay, the equation of the quadric that you get there is a double plane. Okay, so maybe it can be worked out.
Are there any more questions?
I have just a curiosity to ask.
All right.
Israel, it seemed to me that at some point you were looking at this problem. So you have SO4, so anti-symmetric 4x4 matrices, and you have an action on the space of 4 polynomials in 4 variables of whatever given degree is. And then you were trying to look for pairs of a vector in that representation, an element of the algebra that acts by 0. So that vector that is invariant by this element. Was this the problem that you were? Okay. So then, just out of curiosity, so if SO4 is also SO3 plus SO3, and so if you started with, instead of looking at distributions in P3, you looked in P4, you would see this anti-symmetric matrices 3 by 3. So I wonder if I ask you for this problem now, you look at that representation of SO3 plus SO3, and now you're looking at pair of matrices in SO3 that kill this guy. Does it have some geometric translation into distributions on P2?
Never thought about it.
It's just this very same algebraic translation of your problem, but now just going back to geometry, looking into SO3 plus SO3 instead of SO4.
So you take 3 by 3 anti-symmetric matrices.
Yeah, a pair of those is the same thing as a one anti-symmetric matrix, which is 4 by 4.
Yes.
And so the question is, your problem is equivalent to the problem of looking, instead of SO4 acting on this space of polynomials, you look at SO3 plus SO3 acting on this very same space of polynomials. So algebraically, the problem is the same, but now the question is, does it have some geometric meaning the matrices that are 3 by 3 and are anti-symmetric, I can interpret them as distributions in P2 now instead of in P3.
It's not
so now
P2,
you're going to have
the projectivization of the tangent bundle of P2. So you're looking at the contact distribution on the projectivization of the cotangent bundle of P2.
I need to absorb that.
So, any more comments, questions?
Let me just ask Raimundo to send me an email with...
Sure.
Okay.
But it was just a curiosity, it's just some triviality.
Yeah, just to have something I can look at.
Okay.
Okay. And thank you, guys. Thanks a lot for the attention.
Well.
Lovely to see all of your...
No. Let us thank Israel a lot.
You can't imagine how I long... Oh, there is Mauricio now. Yeah, how I long to...
Hi, Israel. Thank you for this nice talk. Thank you very much.
Okay.
I appreciate you.
Bye. Thank you, Israel.
Well, let's thank Israel again. It was such a good talk. That's it.